Today we're very honoured to be joined by Lee Smolin, who's come across to us from the Perimeter Institute in Ontario, Canada. Lee did his a BA at Hampshire College in Physics and Philosophy. His supervisor was Herbert Bernstein. Then he did a AM and PhD at Harvard. His supervisors were Sidney Coleman and Stanley Dresser. His research topics were studies in quantum gravity. He then did several postdocs at including places such as UC Santa Barbara and University of Chicago. And then he joined the faculty at Yale for 4 years, and then has also served on the faculty at Syracuse University and at Penn State. And since 2001, he was a founding member of the Perimeter Institute for Theoretical Physics, which is in Waterloo, Ontario, Canada. Lee is most famous in the physics world for being a co-inventor and significant contributor to the loop quantum gravity. And his research has revolved around quantum gravity and other systems of gravity, such as string theory, investigations of using string theory to understand gravity. He has also been published four books for the public. In 1997, he published The Life of the Cosmos, about the possibilities of black holes evolving by process of Darwinian evolution. Then in 2001, he published the book, Three Roads to Quantum Gravity. And then 2006, The Trouble with Physics. And just most recently, this year, he published Time Reborn, which I see in a couple of the hands of people here. So please join me in welcoming Lee.
Thank you. Thank you. Well, it's very good to be here, and it's a pleasure. I've just spent the weekend at a WOW conference a little bit up the road from here. So I'm in a good mood. And I've also been giving a lot of public talks about the new book, Time Reborn, and this is a variant on that talk. My understanding is that you all are about half scientists and half members of the public, which is not necessarily mutually exclusive, but in any case, just so I get a sense, who is not a scientist? Okay, any among the scientists, any mathematicians? Okay, philosophers? Fellow theoretical physicists? Okay, this talk is not for you guys. Astrobiologists? Okay, SETI researchers? Okay, cool. Okay, so this talk reflects two books, actually, the new book, Time Reborn, and a forthcoming book, which is the academic version of Time Reborn, or an academic variant, which is co-written by a very gifted and influential philosopher, Roberto Manguibera Unger, from Harvard Law School, and which we hope will be forthcoming in a year or so. Okay, now, I write books not as a journalist and not to report established science. So I want to say at the very beginning, I'm a scientist. I work on fundamental problems in theoretical physics, in particular, the question of how to extend our knowledge of physics to unify the great revolutions of the 20th century, quantum theory, particle physics, cosmology, and general relativity. And the revolutions of the 20th century remain unfinished because they're unconnected to each other. And if we want to give one picture of nature, we need a unification of all the knowledge that was discovered during the very fruitful period of the 20th century in physics. So that's what I do professionally. And that work, which is on the edge of knowledge, raises puzzles. Puzzles which in some cases, or at least the ones that I'm interested in, have aspects which are scientific and technical, and aspects which are philosophical. And I found that thinking clearly about the puzzles helps me do my research, helps me focus and steer what I do in the technical side of the research. So primarily, I write books to examine puzzles which arise, fundamental questions which arise, which can't be dealt with in the scope of a research project, a technical research project, or it can't be reported in the scope of a research paper. So I want it very clear, we're talking about the frontier of knowledge, the edge of knowledge, and here. Because it's very important, sometimes people forget to say that, and people go away from public talks thinking that there exist multiple universes or extra dimensions or things like that. Okay, and I'll be very careful to say when there's experimental evidence for anything I talk about, but chiefly we're talking about puzzles. Now, as I've been doing this work, I've become more and more convinced that there is a chief puzzle and a chief confusion that is behind our failure so far to find a correct and experimentally testable unification of what we know about nature, and that puzzle concerns the nature of time. So this talk is about time. And the question that I'm going to be addressing is a very direct and simple one. We all have an experience of the world through moments. Everything we experience, everything we're aware of, everything we think is experienced or thought in a moment, which we experience as one of a succession of moments. Now, there's a very simple question. Is that the way the world really is? Is nature really organized so that everything that is real in a moment, which is one of a succession of moments? Or is that not the way nature is? Is nature organized in some way where when you get to a fundamental description, there's no time, or time is organized a different way within a succession of moments? And our experience of the world through moments in their succession is an illusion. So that's the question that we're addressing. Okay, everybody on board? Okay. Now, science started with time. Some people say that the first scientist was the Greek pre-Socratic Anaximander, and in the only fragment of his which we have directly from him, he says the following: all things originate from one another and vanish into one another according to necessity in conformity with the order of time. So science began with time at the core of our understanding of the world, but has proceeded long since now to the end of time, or the elimination of time. In 1955, shortly before he died, Albert Einstein wrote this to the widow of a dear friend of his, Michael Besso, who had just passed away. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. Now, by that, Einstein meant that if you understand the world fundamentally, then what really exists is the whole history of the world as one. And the distinction between past, present, and future is an illusion. The experience we have of living through a succession of moments is an illusion. What really exists is all the moments of our life as one timelessly, if you get that picture. It's as if you took a movie of your life and laid out all the frames of the film on a light table in order and said, there, that's what's really real. That's the collection of moments which make up life and the order of them. Now, I don't know if this was consolation, but Einstein thought it was, and maybe we can meditate on that. Now, how is it that Einstein came to that view, and how is it that that's been persuasive? So that myself, before I began to think it through, and most of my colleagues, and indeed most throughout the 20th century, of physicists concerned with the nature of time and philosophers concerned with the nature of time, thought that time and our experience of it was in some sense an illusion. How did that come to be? And as I'll argue, why is that wrong? Okay, well, I want to frame the discussion in a little bit philosophical terms, in terms of the idea that the philosophers call naturalism. So is that okay? And this is a framing of the discussion. You know, sometimes you write something and you publish it, and then you realize, oh my God, now I understand the right way to frame this to the public. And that's this case. You won't find this distinction in the book, but that's just because I thought of it while on book tour. And you don't get to go back and change the book. So what philosophers talk about the philosophy of naturalism. Naturalism is the view that everything that exists is part of the natural world that science describes. Okay? And that's a very pervasive idea. And I'm not going to argue it, although I'm not going to assume that all of you believe it. But at least you understand it. It's what's called, in other words, the secular worldview. There's no spiritual world. There's the mental world is not a separate realm. It's part of the physical world, etc. Okay, so let's talk about naturalism. Naturalism comes in two versions, and I want to distinguish them, and I want you to think about the distinction between these two versions that I'll call version 1 and version 2. Here's version 1, and version 1 is the pervasive one. And as I'll argue, it colors our thinking way beyond questions about the nature of time. Version 1 and version 2 differ as to whether you accept Einstein's view that time is an illusion. That's version 1, or you don't accept it, which is going to be version 2. But as I'll develop the next few minutes, this affects our thinking about a lot more than just the nature of time. It affects our thinking about ourselves, as I'll bring forth. According to this picture, almost everything that we experience about the world is an illusion. The solidity of this wood, I hope it's wood anyway, or faux wood, or whatever it is. The smoothness of the air. These are illusions. Things are really made of atoms. And the material, even though it seems to be solid, is mostly empty space. What's really true, and this has been true, this has been believed since the Greeks, since the pre-Socratics, is that what's really true when you break things down is everything consists of atoms, and atoms moving in space, or as the Greeks put it, atoms moving in the void. And according to this picture, what's really real is just the atoms. Everything else is in some sense an illusion or emergent from that. Now to be more specific, the atoms never change. The properties of the atoms, they have masses. Now we would say elementary particles rather than atoms, but let me use the Greek term atoms for that. They never change. They're eternal and unchanging. They move according to laws that never change in a space that never changes. That's what nature really consists of. And everything else has to be explained and described in terms of combinations of atoms and motions of atoms and interactions of atoms with each other. Okay, everything else is secondary or emergent, not part of the description of nature, which means when you get down to the fundamental description of nature, all of our sense perceptions, all the terms that we think about ordinary life in are gone. Everything is just atoms. And science is supposed to consist of the reduction of everyday phenomena, observable phenomena, to the motion of atoms. Now, the laws by which the atoms move around and interact are described by mathematics, by mathematical formulas. You may have studied, and if you're a member of the public, if you're not a scientist, you may have studied this last time in high school, but you wrote down F equals ma, force is mass times acceleration, or a falling body has a constant acceleration. These are all mathematical expressions of laws. The way this pans out when it's fully developed is the following way. The positions of all the atoms can be observed, and the motions of all the atoms encoded into mathematical expressions. You can give the positions in terms of a set of numbers. You have a reference point so many centimeters to the left, so many centimeters above, and so many centimeters behind the reference point. It gives you the position of the atoms. So the state of the world, if the world is nothing but the position and motion of atoms, that's translated into a whole bunch of numbers, into a mathematical expression. There's another formula that is the expression of the laws. It tells you, given the positions of the atoms and their motion at one time, how are they going to move into the future? And that's a mathematical expression, whether it's Newton's laws or Einstein's equations or quantum mechanics. It's a piece of mathematics. The output is another bunch of numbers which tells you where the atoms are at a later time. So in a modern way, another way to talk about this is computation. Okay? It's as if the laws of nature are a computer program. What does a computer program do? A computer program acts on input to produce output. That's what a computer program does. It's a fixed set of rules or algorithms that acts on input to produce output. What's the input for the laws of nature? It's where all the atoms are presently and how they're moving presently. What's the output? It's how all the atoms are moving and where they are at a later time. So we can think of the universe as a computation, as a piece of a computation carried out by some big computer, or equivalently, as a piece of mathematics. This is what I say on this slide. This time is emulated by a computation. Okay. Now, are you all with me? This is naturalism version 1. The world, most of what we see and experience in the world is an illusion. The world is really emulatable completely by a computer program. It's great to be talking about this in Silicon Valley because there's very wealthy and powerful corporations which are run by people who believe this stuff. Maybe some of you are here or listening, so this is addressed to you. There's not just believe that this is useful, but that this is the metaphysical truth. The world could be replaced by a computer program and nothing would be lost. This means that time is not fundamental, because time is the process that evolves, given the present, evolves you into the future. And if that's completely emulatable by a computer program or a piece of mathematics, then the question about the relationship between the present and the future is a logical relationship. It's something that could be carried out in a series of logical steps, because all computers do is carry out logical deduction. All mathematics is the process of logical deduction from an input to an output. And logic is outside of time. Logic, if a logical deduction is true, it's always true. So the world, according to this view, can be emulated by a description in which time is replaced by logic, in which the relationship between the present and the future is a relationship of logical implication, and therefore outside of time, because if a logical implication is true, it's always true. So this is the sense in which time is an illusion. This is what Einstein was arguing from, that the distinction between the past, present, and the future is an illusion, because it's just the same facts rearranged by logical deduction. Okay, I'm saying, I hope it's okay, I'm saying what I'm saying on the slides, but slightly differently. But if you can read the slides and listen to me both, that's good. If you can do one or the other, that's probably good enough too. Okay, now according to this picture, fundamentally nothing happens except the rearrangement of atoms. So nothing new ever happens in the world. Novelty is an illusion. The impression we have, if you're an artist or an entrepreneur, or in so many ways of everyday life, in which you invent something new, you come to a new idea, a new realization, a new song, a new painting, a new business idea. This is all an illusion, the sense of novelty of never having existed before, because it's all just a rearrangement of the past. Not only that, the computer program, given an input, always gives the same output. The laws of physics are what are said to be deterministic. If somebody wants to raise their hand and ask me about quantum mechanics, do so later. Because we're going to talk about quantum mechanics. So the notion of free will is impossible. And this is a very commonly believed thing, that free will is an illusion. Why? Because all that's going on in the brain is chemistry, which is just atoms moving around. The laws are determined. The initial state was determined, it was set a long time ago. So you may think you make a decision, you may think that you make choices, but actually you never had any choice about the choices you make because your brain is just atoms moving around. And people believe this so much that they fool themselves to thinking that there are experiments that verify it, like there's a kind of badly interpreted experiment in which they do brain scans and they see something happen in somebody's brain half a second before the person experiences themselves making a choice. And they think, aha, therefore the experience of making the choices that you didn't really make. Well, I can't articulate what they're trying to say because it doesn't make any sense to me. But there's an argument that you don't have any free will because something happens in the brain that's observable by a brain scan before you experience yourself making the choice. Okay. Now, does everybody here know Tom Stoppard's play Arcadia? Tom Stoppard is one of our great living playwrights, and Arcadia is one of his recent plays. Has anybody seen it? Good. So in Arcadia, there's a character called Thomasina, who is a young woman who is brilliant, who's a prodigy, and she has a tutor. And she says this to her tutor one day. And this is just an expression of this point of view, and just an illustration of how prevalent this is. It's even in theater. If you could stop every atom in its position and direction, and if your mind could comprehend all the actions thus suspended, and if you were really, really good at algebra, then you could write the formula for all the future. That's what I've been saying. And now the next two lines are why Stoppard is brilliant. This made me appreciate that he really is a deep thinker and really understands the issue. She goes on to say, and although nobody can be so clever as to do it, to write that formula must exist just as if one could. That is, even if it's practically impossible to write the computer program that expresses exactly the laws of nature, and even if it's impossible practically to measure enough data to determine completely the future by running it through the laws of nature expressed in the computer program, okay, the mathematical formula for the laws of nature must exist. And the mathematical expression of the future must exist anyway, just because of this philosophy of nature, that what really exists is atoms moving which are expressible mathematically. Okay? So according to this view, if that formula exists, as Thomasina says, then the future already exists. Because the formula is the formula for all the future, as she says, as she calls it. And if the formula for the future already exists, then the future does exist now. We just haven't experienced it yet. That's a minor thing. As somebody said in a discussion yesterday, why are you worrying about a psychological peculiarity of one species on one planet to have this crazy thing of believing that they experience the world through time and therefore believe that they make choices and invent novelties and have ideas and things like that? Okay, the world really is just already fixed and the future already exists because what really exists is the mathematics. Okay, you get it? This is where we've come a long way from nothing exists except the physical world. Okay, we've come a long way, but this is where we are. I'm going to skip that because I said that. If the evolution of the universe is equivalent to a computation, then the experience we have of the present moment is an illusion. A mathematical formula simply is. Mathematical formulas don't live through a series of moments, they simply are. Mathematics is not, if a mathematical deduction is true now, it was true 1 billion years ago, it will be true 1 billion years from now. The truth of a mathematical expression, most philosophers and mathematicians are convinced, has nothing to do with the experience human beings have of working through the logic of the proof. So if we reduce the description of the world to mathematics, then time is an illusion. Now, some people take this really far. My friend Max Tegmark, who's a brilliant cosmologist but likes to get a little bit crazy when he speculates, talks about the mathematical universe hypothesis. Because now we have a problem if you like your philosophy clean and tidy. If there's the universe and there's a mathematical expression of the universe which is equivalent to the universe, why are there two things which are equivalent to each other? the universe and the piece of mathematics is equivalent to it. Maybe what's real is just the piece of mathematics. Do you all follow blogs? Sabina Hossenfelder is a professor in Stockholm, a physicist, and she has a very, very widely followed blog, and this was her response to it. Tegmark says the whole universe is a mathematical structure. So he must believe that he is a mathematical structure as well. And I am a mathematical structure too. I wonder what it feels like being a mathematical structure. And that's the key question, because what's the relationship between what we experience, what we feel, and this allegation that we're really just mathematical structures which are part of a larger mathematical structure? So that's the puzzle. Now, another aspect of this is this idea that time is just another dimension, which you've heard over and over again, the fourth dimension. The time is another dimension. This is, in popular accounts, this is said to come from relativity. But here's a quote from H.G. Wells in the 1880s or 1890s, which preceded Einstein's discovery of special relativity in 1905, which he says there's no difference between time and any of the three dimensions of space except that our consciousness moves along it. So this exists as moving along, and implies it's like riding down a road, but the road is already there. This is again this picture of the whole universe already existing in time, and you just experience it like looking out the window going down a road, driving down a road, but it's already there, the path. Okay, this is naturalism 1. Okay, have I scared you enough? Now, I'm just going to go off the record here, since I am in Silicon Valley. And I'm going to emulate my friend Jaron Lanier, if any of you know him, and worry about the fact that we all spend a large part of our days connected to technology, which are computers, which run computations, and interacting with each other. Our interactions are more and more mediated by computation. The computation is fine, it's a tool, but if there's this metaphysical picture in which the universe is really a computation, and we are really computations, then if something's missing from that picture, maybe some things about us will be missed by the technology which is increasingly dominating our lives. So that's just a worry. That has nothing to do with this talk. But can I mention my other worry about Silicon Valley while I'm here? Why, if the smartest people in the universe who built this technology that dominates the world made Silicon Valley, why did nobody ever consult an urban planner? If anybody knows the answer to that, tell me afterwards.
Because they don't know how to program. What other skill is there?
Okay, now Einstein was actually ambivalent about this issue. I already quoted him, the distinction between the past, present, and future is only a stubbornly persistent illusion. But here is another report of Einstein's worry about what is missing in this picture. This comes from Rudolf Carnap, who is a philosopher who was a friend of Einstein. And the subtext, which is suppressed because these guys were serious Central European intellectuals, so I didn't put in the part about how they went out drinking all the time. This is what they talked about when they were drinking. But it's like, you know, if you were an undergraduate and went out drinking with your friends and worried about the nature of the world, you would worry about this. So once Einstein said that the problem of the now worried him seriously. He explained that the experience of the now means something special for human beings, something essentially different from the past and the future, but that this important difference does not and cannot occur within physics. That this experience cannot be grasped by science seemed to him a matter of painful but inevitable resignation. So something is missing. It's everything connected to the now, to the fact that we live in a series of present moments. And Einstein thought, this is the last sentence I'll read, that there is something essential about the now which is just outside the realm of science. So Einstein was disconcerted by the disappearance of the now from the description of nature that he had helped to make. And this is my turning point in the book and in the talk. By the way, can you see that there's an ambiguity in that last sentence? Just outside in English has two meanings. It could mean is just outside, as in it's unavoidable, it's far outside, it can't do anything about it. And it could be just outside, as in just across the street. And I wondered which Einstein meant, and I consulted a German friend who consulted the original, and unfortunately it means the first. I thought it meant the second, and I was willing to build some hope into that, but anyway, where I want to go to, let's just pretend that Einstein meant the first, that the experience of the now is just a little bit away from the boundaries of present science, and let's try to bring it just inside the boundaries of science. That's what we're going to do now. That's what I'm going to tell you about a program to do. Okay, so this is where version 1 of naturalism ends up. And let me just emphasize, in a world in which the experience of the present moment is an illusion, a whole lot of other things are also illusions. Free will, novelty, agency, imagination, values, all these things are all illusions. In other words, the things we care about are wiped out of the fundamental description. We're so used to this that we don't think it's weird. That we ask the physicists, myself included, to give us a story of the world in which we fit a picture of nature. We want to believe this story because it comes from science, and science is based on reliability and testing. And then they give us a picture in which the things we care about have no place. Is that a problem? Steven Weinberg expressed it this way in his book, The First 3 Minutes, his first book: the more we know about the universe, the more pointless it seems to be. Okay? So, I think there is a problem, and since this is largely a popular audience, I'm giving you the implications of the science before the science. But I think there is a problem with this construction of the natural world internal to science. I think it's the reason why we have so far failed to unify general relativity with quantum theory and find the correct unification of physics. And the arguments that I have for that are mostly scientific and mostly technical, and I'm going to protect you from that mostly, although I'm going to give you a sketch of those arguments. But I wanted to give you an understanding of what, in my point of view, or in my opinion, is at stake in this issue. Okay. Now, to disprove that nature is completely equivalent to a piece of mathematics, I just have to give one property that nature has that no piece of mathematics has. That's all I have to do. And it's not hard to do. No piece of mathematics has moments. No piece of mathematics has moments which are successions of moments. Because if a mathematical object, as the mathematicians call it, or a piece of mathematics or a formula, if it embodies some mathematical relations, if they're true, they're always true. They're true timelessly. But here in the real world, it's always some moment. It's always some present moment. If we believe that that's not an illusion, then the world cannot be equivalent to a piece of mathematics. Hence, version 1 of naturalism is wrong. Okay. Now, I wouldn't be taking your time and standing the whole argument on that one piece of logic, because if you're committed to this view of nature, you just believe already that everything about our experience is an illusion. Okay, but again, this points to what's at stake. And now let's talk about why this view fails, not just on logical grounds, and not just, if you like, on moral grounds, but on scientific grounds. And there's a particular issue, a particular reason why it fails. And this is a little bit sophisticated, but I'll try. I think it's easy to understand. Okay. Science is all about what happens in laboratories or in isolated systems. Now here, there are a lot of astronomers and astrophysicists, and they study big systems out there in the universe, but still small parts of the universe. A galaxy, a star, a solar system, especially here, solar systems are under study. Okay. These are studied as if they're disconnected from the rest of the world, as if you could draw a boundary around them and study them in isolation. Okay. And the use of measurement that is standard, in which we take a series of observations and record them, implies that there's an observer who's outside the system doing the measuring and doing the recording. It implies there's a recording device which is outside the system doing the recording. So the standard methods of physics and astronomy and the rest of science as well imply that you're studying a small part of the universe, isolated. Nothing is really isolated from the rest, but idealized as if it is isolated from the rest. Now, the use of mathematics in this context is obviously the right thing to do, because you make a series of observations. Say the Kepler satellite looks at a system, a planetary system, the stars and planets, and makes a series of observations of the light coming from that system at a series of times, and those observations are stored in records, and then they can be modeled by a piece of mathematics. Now, the records don't change in time once they're stored. They're just a record of things that happened in the past. And if they change, that would be a problem. They would cease to be reliable records. And the mathematics, as I've said, never changes. The pieces of mathematics don't change. They just are. So it makes sense to use a piece of mathematics to emulate the data or the record of an observation of an isolated system, of a part of the universe. So that's the method of physics, and it works crazily well. It works awesomely well. But there's a caveat. It works when you've treated a part of the universe as if it were isolated from the rest. And the observers and the measuring instruments and so forth are outside of it. Now, the mistake that I think has led us all to this crazy metaphysical picture in which there's no time, in which the world is just mathematical, comes from taking this method, which is highly useful, and applying it, upping the ante and applying it to the whole universe. That's the mistake. And there are 5 different ways. I'm not going to give you all of them, but there are 5 different ways of making a case that if you forget the limitations of that version of a scientific method, and try to apply that kind of modeling to the whole universe rather than a small part of it, you're making a series of errors. Errors of method, errors of logic. You're doing something fallacious. Okay. So that's the short version, that's the outline of what the issue is. If you don't do that, then you have to start again and figure out how to make a description of nature that makes methodological, that's a fancy word meaning there's a practical way to develop it and get experimental predictions that can be applied to the universe as a whole. And my main claim is that that requires putting time back in the center of the story. And I call that version 2 of naturalism. It's a different way of conceiving of the natural world as in a way that doesn't eliminate time but centers on time. So the metaphysical implications of the version 1 were based on an unwarranted extrapolation and therefore fallacious reasoning. Okay, and I just said that, but just to emphasize that the main fallacy is taking a method good for studying parts of the universe and applying it to the whole universe. We call that in our work with Roberto Unger, the philosopher I've been working with, the cosmological fallacy. Now, here's a way to frame it, which I call doing physics in a box. When we study that planetary system that Kepler might be looking at right now, we imagine that we could put that planetary system in a box. It consists of a star some number of planets, and a whole lot of other stuff that we idealize away because it's too small to affect what we can measure. And it is influenced, however mildly, by distant stars, by gravitational waves coming from afar, by very energetic radiation coming from afar, and we ignore all of that. We pretend that the system is in a box. Now, I'm talking about Kepler because I'm here at SETI, but in every instance in the laboratory, as a chemist or a biologist or a physicist would do it, we actually construct the box, and we work hard to eliminate the influence from the outside on the system of the box, and that's called going down the noise. That's called suppressing the noise. So I claim that doing physics in a box is the basis of the method of science applied to small parts of the universe. And there it makes sense to talk about laws which don't change during the duration of the measurement, acting on... Remember I talked about atoms, which properties that don't change, moving according to laws that don't change, in a void which doesn't change, in a space that doesn't change. Here's a little bit, I'm just saying the same thing in different words. When you have a set of possible configurations that the planetary system could be in, all the possible positions of all the planets with respect to their star, that's what you start with. You work in an idealized space of all the possible positions of all the planets there, and you apply Newton's laws to that to give you orbits and describe orbits and correlate that with what you can measure. And that way of doing science in which you have a possible set of states or configurations of the system which are evolved by laws, and neither the possible states nor the laws change in time. That is the set of possible. It doesn't happen that you evolve the system for a while and you discover, oh my God, there are some new states that we didn't think about before. It doesn't happen in physics and astronomy. It happens in biology all the time. That's called speciation. Okay, this we call the Newtonian paradigm, which is another way of talking about physics in a box. I'm just trying to be pretty precise about this claim that there's a method of physics which is highly successful, which you're just dying because of its success to apply to the universe as a whole, but if you do so, you'll make a fallacy, you'll make a methodological error. I'm just trying to be precise about this and give you a sense of what's at stake. This is what Thomasima was talking about, observing a system from the outside, measuring the positions. Here I'm using atoms rather than planets, but it's the same thing. Writing the formula of the computer program that emulates the system. Then you study how particular initial configurations evolve by running the computer program that emulates the system. And that's how you get the future from the present. Now, can we put the whole universe in the box? You know what I'm saying. No. That was Thomasima's mistake. That's why she thought there was a formula for all the future. That's what Tom Stoppard, in his play, in which Thomasima was a character, was trying to argue for, I think. But we could have that discussion offline, what it was really about. Now, I said there were 5 different arguments why this is the wrong thing to do. Okay. Here's one of them. There are big questions that remain unanswered if you put the whole universe in the box. Science comes to a halt because there are questions we would like to answer. There are questions we need to answer that we cannot answer. When we put the whole universe in the box, that is, apply standard physics methods to cosmology. And these are real crises. Each of these 2 questions I'm going to mention is the source of a huge crisis in cosmology and physics the last several decades. The first is, why are these laws the laws? I said the input to the method is to say what the laws are. I've been always talking about these laws which evolve the atoms, which move the atoms about. But why are these the laws? If you want to give a complete explanation of something, is it enough to say, here are the laws, we apply them to the system, and that explains it? If I throw something in the air, it falls, that's Newton's laws and Newton's law of gravity and Newton's laws of motion. that explain it? No, you want to know why are Newton's laws true. If you explain the results at the Large Hadron Collider at CERN in terms of the standard model of particle physics, which is holding up very well, thank you, is it enough to say that every experimental result from every particle accelerator is explained by the standard model of particle physics? No. We want to know, why is that standard model correct? That standard model describes a whole zoo of particles interacting by three basic forces. We give as input to that standard model the masses of all the particles, which forces exist, what the strengths of those forces are, why those forces, why those strengths of those forces, why those elementary particles, why they have the mass charges they do. All of that is in the why these laws question. And if the laws are input to the method, we have no answer. We have no methodology for attacking this question as scientists, because the laws are assumed to start the method off. And there's 40 years of failed attempts to somehow get at this question without going outside the framework that we use, that I've been describing as physics in the box. And I have hours worth of stories, many hours worth of stories about that disaster. Here's another big question. Why these initial conditions? If I want to use the laws to tell me what's going to happen when I collide two protons at the Large Hadron Collider, I have to set the process in motion. That's choosing the initial conditions. That's where the particles are at the present. I said if you could, Thomasima said if you could give all the positions and motions of the particles now, you could use the laws of physics to give all the future, to predict the future. But you have to give them now. That's called the initial conditions. Okay. Now, in an isolated system, in the laboratory, we choose the initial conditions. We experimentalists choose the initial conditions. There's no mystery about why these initial conditions, because we wanted to choose them and study them. But in cosmology, let me take, before I get to cosmology, in astronomy we don't choose the initial conditions, but we see lots of different systems, and we get to study what happens when the initial conditions are different. We study lots of galaxies, lots of stellar systems, lots of planetary systems, and we have a whole lot of different systems with different initial conditions, all obeying the same laws to play with and to study. When it comes to cosmology, there's just one case. There's just one set of initial conditions, and we didn't choose them. Not only that, but everything we know about cosmology is leading to a bizarre conclusion that the initial conditions shortly after or at, quote, the Big Bang, which is allegedly the first moment of time, are very, very, very hard to understand. They're not, if you took the laws that we believe are operating, and you said, what's a typical initial condition for a universe running those laws, we wouldn't get anything like our universe. To get anything like our universe, which blows up nice and big and smooth and regular, in which the laws of thermodynamics work, in which there's a big arrow of time so that life can exist, in which there are long-lived stars, all these things depend on very delicate choices that were apparently made at the initial condition. And that makes you nervous to hear a scientist talking about choices being made at the birth of the universe. I'm deliberately trying to make you nervous. Because that's what people end up talking about. One way that people say it is that the initial conditions were very improbable at the beginning of the universe. But that's weird. The universe is the only thing that exists. It's one case, so how can anything about it be improbable? If you have a story in science that leads you to say that the one thing that exists is improbable, you probably don't have the right story. Okay, so why these laws and not others? Why these initial conditions and not others? This is some of the problems. These are some of the problems. You can't ask a computer program to explain why it's the computer program which is running, or to explain what its inputs are. You can't ask the standard method of physics to explain why these laws and not others. Now, I have several other reasons. I'm going to skip. I hope you don't mind. I'm skipping quite a bit because I noticed that I have like 5 or 10 minutes. And I want to skip to this. I hope that's okay. And I apologize, but if I talked for 2 hours, you would not be happy. I'm not the first person to worry about the why these laws problem. It turns out that the great American philosopher Charles Sanders Peirce worried about it already in the 1880s and the 1890s. Have people heard of Charles Sanders Peirce? He's said to be the most important and greatest American philosopher. He's got quite an interesting life story, but I'll skip it. And Charles Peirce had this to say: to suppose universal laws of nature capable of being understood by the mind, and but yet having no reason for their special forms. In other words, to assume that there are laws of nature which are just true, standing inexplicable and irrational without explanation, is hardly a justifiable position. I'll skip a sentence. Law is par excellence the thing that wants a reason. It's not enough to explain what happens in terms of laws we posit. We have to account for the laws themselves. Now, in red, the only possible way of accounting for laws of nature and for uniformity in general is to suppose them the results of evolution. This is the big idea which is at the heart of this new version of naturalism, this naturalism version 2. The laws are not eternal, the laws are not immutable, the laws change in time, and because they change in time, they have a history, and that history renders them explicable in a way which science can address, because if the laws have been different and have changed through processes that acted in the past, then there might be fossils of those processes that acted to change the rules, the laws. There might be consequences for observation because we're talking about things that happened in our past. And astronomers are very good at delving more and more deeply into our past. So that's the big idea, that the laws change. And if the laws change, then you can't make a mathematical emulation of the universe if the laws have the possibility of changing. And the future may not be completely determined from the present. So it seems at first that you lose something for science by taking Charles Sanders Peirce's point of view. But as I'll argue, you gain. You can, we'll have a lively question discussion. Well, let me just address it now. You raised the question of whether if the laws change, there's a meta law, another law by which they change. If I don't address that in the next 5 minutes, raise your hand or just ask me again. No, that's the key question. I just want to build up to it. Now, I came to this view in the late 80s through my own peculiar thing. It would have saved me a lot of time had I been decently educated the way that scientists should be and known of Charles Sanders Peirce. I also didn't know that other philosophers came to the same view. I won't read this quote, but this is a quote by the philosopher I now collaborate with on this. I'll just read the last line. People who appeal to fixed conceptions of necessity, contingent, and possibility are simply confused. Turns out a number of really great physicists have had this point of view as well, although it's not often emphasized. Paul Dirac, at the beginning of time, the laws of nature were probably very different from what they are now. Thus, we should consider the laws of nature as continually changing with the epoch instead of holding uniformly. Even Dick Feynman, and I wish I could do the Brooklynese of Richard Feynman, but I'll sort of try to give you the informality. This is in a video that you can find online. He worries the only field which has not admitted any evolutionary question in physics. He notes before this quote that all the other sciences other than physics have a historical aspect. Astronomy and astrophysics have a historical aspect. The universe is changing in every era, and there's a history to it. Biology is historical. Physics is the only of the major sciences which is fundamentally, even chemistry is historical because the chemical elements are evolved and made in the history of the universe. Physics is the only field that doesn't have an evolutionary or historical component. Why? Feynman says, here are the laws, we say. Here are the laws, but how did they get that way in time? So he concludes, it may turn out that they are not the same laws all the time, and that there is a historical evolutionary question. The interviewer goes on to ask him, so, Dick, how do you do that? And he says he has no idea. Okay, now John Wheeler, one of the great American physicists also, and Richard Feynman's PhD advisor, somebody who should be better known, also speculated about this and used to talk about reprocessing the universe. He used to imagine that universes are born in black holes, that when a star collapses to a black hole, rather than time ending in a singularity where the star gets squeezed down to infinite density, some quantum processes intervene and cause a bounce where that region of space starts to expand again. But it's not in our present universe, it's to the future of our present universe, so a new universe is created. And he used to call that reprocessing the universe, and imagine that when that happens, the laws of physics changed. This is early 1960s. So it's not just me who thinks that we should examine the idea that maybe the laws of nature change. Now, you can get this far by general philosophical argument, or a critical argument, thinking critically about the state of science, where it is, what the problems are. Okay? But to go further, I want to do science and not philosophy, although I gain an enormous amount from talking to philosophers. And that requires verifiable and falsifiable hypotheses. Science proceeds by people postulating hypotheses which are checkable. And so if this is worth anything, I and other people have to be able to come up with hypotheses about how the laws could evolve in time or might have evolved in time, which have implications that are checkable. That's my job as a scientist. And in the next hour of the talk, which I won't give, but I want to mention in case anybody wants to ask about them, there are two directions, well, there are several directions that I've explored, and there are two of them that I'd like to mention. One of them, called cosmological natural selection, which is a development of John Wheeler's ideas that new universes are born from black holes, and amends his hypothesis in one small way to make the changes of the laws on the birth of a new universe to be very small. In terms of those numbers that I talked about in the Standard Model, the masses of the elementary particles, of the quarks and the neutrinos and so forth, the charges, the strengths of the different forces. Imagine that, now there are about a billion black holes in our observable universe as far as we can estimate. Imagine that each one of them is the birth of a new universe. And in each one of them, the laws are pretty similar to ours, but those numbers have been changed, nudged by small random amounts. That's the only change that I made, that small random amounts to John Wheeler's hypothesis. And then it turns out that you have a story which is amenable to treatment by the methods of biology, and evolutionary biology in particular, because it then follows that some universes have parents which have lots of black holes, lots of progeny, and some universes have parents which have few progeny. But a typical universe is going to have parents which are very prolific, and grandparents which are very prolific, and so forth. Just like in biology, we're all the descendants of billions of years of evolution in which creatures had progeny which thrived. That's what we are. That's why we're so well fit and so well tuned. And so a typical universe in the story must be highly tuned to produce new universes, that is, to produce black holes. And that leads to a series of hypotheses that can be examined and checked. And I'm not going to take you through that because that takes you through some detailed astrophysics. But that's one such idea. And that idea, just since there are astronomers here, let me put back on the record one of the two predictions. Well, since I mentioned there are two, I should mention both of them. Predictions that were made in 1992 when I first published this. And I won't explain this, but the first prediction is that there should be no neutron stars more massive than twice the mass of the Sun. And that's a prediction that seemed unlikely when made, because estimates for the largest stable neutron star were coming in at about 3 to 3.5 times the mass of the Sun, making standard assumptions. And that's a story I can tell if people want me to tell. But it has held up. Recently there's observations of a neutron star at 1.99. Well, the second 9 is probably gratuitous, 1.9 solar masses. And there's also one of 2.1 plus or minus 0.3. So it's just holding up. Okay. So, but if the theory were proved wrong by the observation of a 3 solar mass neutron star, that would only demonstrate the point, which is that this is science. Because you can have hypotheses about how laws evolved which are checkable. The other one has to do with inflation and is also held up through the recent Planck data, but it would be a technical thing to describe it. Again, somebody can ask me. The second idea is more recent. The second idea about how laws evolve is more recent and is called the principle of precedent. And I think I should just characterize that in one sentence and then conclude, because we're running on time. But this is idea, let me just describe it this way. If you do a set of experiments now, and you get some distribution of outcomes, you do some set of experiments later, you expect to get the same distribution of outcomes, right? Because experiments are repeatable. Why are experiments repeatable? Well, experiments, the standard view is, well, they're laws of nature, they're always true, they hold in the past, present, and future, and they govern motion, and therefore they will give you the same result. The laws acting will give you the same result in the future as in the present and the past, and that's why experimental results are reproducible. But maybe experimental results being reproducible is just the principle. That is, maybe what nature does when you challenge it with an experiment is look to past instances of that challenge and produce the same result. Maybe that's the law of nature. And if that's the law of nature, it's checkable because people in laboratories building quantum computers are making systems, quantum systems that have never been studied before, for which there's no precedent. And since this is SETI, let me just amend that slightly and say for which there's no precedent so far as we know. And stop there, and thank you.
Lee, if I could ask the first question, and then I'll pass the mic around to people who put your hand up if you've got a question. So in your book, the principle of precedence, you talk about how for a simple particle, things are likely to have happened many times, and so those things should be laws over time because they've happened in the past. And this does this give us some sort of agency because we're more complex and perhaps we haven't happened before, and so the laws surrounding our future are more open, shall we say. But then the counter to that is that we're made up of these particles in the universe that have made their decisions in the past, and so we're following along in a rut. Where the particles about
so
what
Adrian,
isn't.
let me duck that question. and replace it. You know, politicians, I'm not a politician for sure, but politicians, the skill of a politician is they answer the question that they want it to be asked. So, so there is the possibility to speculate that in the brain there are processes which are novel, which are not subject to precedence, and that explains something about intelligence and so forth. Okay, but most attempts to try to tell a story about quantum effects in the brain have failed. I mean, Roger Penrose and Stuart Hameroff and so forth have famously failed going down that road. So I will only go down that road very carefully in collaboration with good neuroscientists. Okay, but well, no, I'll come back to, somebody is bound to ask me the question I want to be asked.
This probably isn't it. So my understanding is that in order to get a universe that can have electrons going around nuclei and form stars and therefore black holes, you already have to tweak the initial conditions pretty thoroughly. So if your evolutionary hypothesis about universes emerging organically from black holes is true, how did we get the first black hole?
No, that's a very good question, and I don't know the answer to that. No, it's very important, of course, in science to be able to say, I don't know the answer to that. What is testable is universes with parameters. You can tell not a compelling story, but a plausible story about what the universe would be like if we made small changes in the parameters of the laws. And I'm happy to test the idea by just studying the effects of small changes and see if there are any small changes that increase the rate of production of black holes. Going way away, it's just too hard to answer your question. But it's so implausible. The standard model of particle physics has 30 parameters. And if in 20 years nobody has produced an argument for how varying any one of those parameters could increase the number of black holes strongly, I take that as remarkable. It doesn't mean I believe the idea is true. But there is a good case to be made that the present laws and the present values of the parameters of particle physics do at least locally extremize the number of black holes. At least there's about a dozen cases in which that seems to have changes in which that seems to be really true. And the others, either we don't know or the changes are neutral. Anyway.
I've got a question here. I'm not a physicist, but you used the word evolution or evolutionary. To me, that brings up the question of what drives. Where do you get a direction? How is a direction established? In the case of a Darwinian system, which we're familiar with, you know, it's predators and environment, and ultimately it gets down to base pairs in nucleic acids and chemistry. If that's the correct, if that's a parallel that you're using, what is the drive? What provides the direction in your model of the universe or of existence or whatever the word is?
This is not a complete analogy with natural selection in nature. It's a formal analogy which only uses one property, but it's a sufficient property, which is that after natural selection has been operating for a long time, a typical member of the population has parents which have large number of progeny compared to others. That's all that I'm using, and there doesn't need to be a drive. Now, I could turn into my Richard Dawkins emulation, argue with you about whether there's a drive in evolution anyway. But luckily, I don't have to do that, because Rich is really hard to...
There's a metaphysical or sort of supernatural suggestion in my mind to what you're saying. I will feel bothered by it.
No, but there needn't be... Then the whole point is that natural selection doesn't drive anything to the future. All it does is say that those genes that produce creatures that have progeny that thrive are more common in the biosphere. That's all it says.
So thriving, what is the equivalent?
Thriving just means, sorry, There was a comma there in my sentence. I wasn't saying two things, thriving and have more progeny. The definition of thriving is to have more progeny.
Lee?
Yes.
Radio astronomers have tried to set constraints on the changes of fundamental constants.
Yes.
Going back in time. Is there any success there that says that that's pointing to, well, if the laws are evolving, they can only change when a new universe is born? Or are we getting any kinds of constraints?
Well, we are getting good constraints, but remember the hypothesis that I took on was Johnny Wheeler's hypothesis that the laws change at a bounce event. Okay. You might ask, and many people have asked, and for example, I was talking with Paul Davies yesterday. You might ask whether the laws change during astronomical time, during time scales of hundreds of millions and billions of years. And my understanding is that there is weak and disputed evidence from the group of Webb in Australia that, and I'll try to say this non-technically, they look at light from quasars. And when light from a quasar passes through a galaxy, the sum of the light at specific frequencies is absorbed by inducing transitions in atoms and molecules in the galaxy that is passing through. But that is at a redshift, that light is redshifted when it then comes to us. And so from where that little chunk is taking out of the light, by absorbing these patterns of chunks, you can see at what redshift that absorption effect took place. By studying many lines at a given redshift, you can ask how a few of the fundamental constants may have changed with redshift. And the evidence is at a level of about a part in 100,000 at a redshift of 2, is what I'm remembering, something like that. But it's disputed. There are other groups which dispute it, and they also don't seem to get consistent effects in looking in different directions. So it's an open issue. It's a very hard measurement to make. But whether that's true or not doesn't affect the hypothesis that the change is made at the Big Bang. There are also other attempts to study the possibility that the gravitational constant might have been stronger or weaker, which were carried out for decades in response to that thought of Paul Dirac that I quoted. And there's no evidence that the gravitational constant changes over time scales of at least, I don't know, small redshift, about 100 million years. Yes?
Sorry,
So I'm trying to, over here,
Okay.
trying to figure out a concise statement of naturalism version 2. So is it naturalism version 1 plus the laws change?
No, I skipped that. Thank you for asking that. Natural version 2 is everything that's real is part of the physical world. Everything that's real is real in a moment of time, which is one of the succession of moments. Every scientific statement that has truth value which concerns the properties of a moment of time. Everything else, including generalizations, laws, are true at a given time and can change, even if very slowly. Sorry, I didn't say that as eloquently as it's on the slide that I skipped, but that's naturalism version 1, version 2. I'll try to find it while somebody asks the next question.
Okay. My question is on the subject of emergence that you touched on. Robert Laughlin recently spoke here at SETI on the need for understanding of emergence in physics as well as in other domains. So I was wondering, do you see agreement between your views and those of Laughlin? And is there a growing challenge from within physics to the simplistic reductionistic dogma that might be another avenue of attack?
Laughlin, Bob Laughlin? I enthusiastically endorse some of the things he says. I don't know what he said here, of course, but I don't take it as far as, I think it's true that much of the phenomena that we observe in nature is emergent. I think that space is probably emergent, that gravity is probably emergent, so I would up his ante in terms of what might be emergent. But I think that time is not emergent. So I think that there is at least one pervasive aspect of nature that we have a direct experience of, which is not emergent, which is time.
Yes, Andre Linde was here not long ago, and he described a different method for many new universes being formed by spontaneous inflation. And from what you say, another selection among that sort of ensemble of universes might be our existence. That is, that we are conscious, we must be here to watch it, and presumably many other universes weren't suitable for our presence.
Yeah, so I'm afraid I don't agree with Andre Linde, and my reason is a complicated discussion, but it's easy to state. In eternal inflation, there are an infinite number of universes which are produced. An infinite subclass of those have properties very similar to our universe. Whatever property you want to name me a property. An infinite number of them share that property. But an infinite number of other universes in the ensemble of eternal inflation don't share that property. So the ratio of universes that share that property to universes that don't share that property is infinity to infinity, which is undefined. 20 years of attempts to define that ratio by various auxiliary hypotheses and so forth have failed to lead to a convincing way to define that. Not only that, you can claim that the anthropic principle, which is what you're quoting, is a way to do that. The anthropic principle is the claim that you should restrict the ensemble to universes that contain intelligent life. But even in that case, you can take some other property, say the mass of, I don't know, the K meson, which affects the upper mass limit of neutron stars, or the dark energy, or the overall size of the universe. And there will be an infinite number of universes that have those properties, and that share that property with our universe, and an infinite number of universes that don't. So the anthropic principle is neither necessary nor sufficient to result in anything which is testable and anything which is well defined. The difference with cosmological natural selection is I only need to argue about typical members of the ensemble. I only need to use the property that typical members of the ensemble are children of parents that had many progeny for many generations. And that's all I need. I don't need to use any special appeal to the anthropic principle. And therefore, I can get predictions such as the ones I mentioned. And just to be, if Andre's listening, we do argue vociferously about it, but let me challenge Andre again. There's just not a single real prediction that's ever come out of that, and it's 30, 40 years of that kind of speculation. And at this point, the right person to quote is not a philosopher, although there are philosophers to quote, but the rock and roll stars, they might be giants, talk about, they have a song called Science is Real. And they sing, my 6-year-old listens to this, many nights. And it goes something like this, I love those stories about angels, unicorns, and elves. I love those stories just about as much as anyone else. But when it comes to knowledge, the truth is with science. The difference between fairy tales and science is what you can test experimentally. Sorry if I went on a little bit heavy, but Andre would do worse if you asked him about me.
So I have a question regarding the example where you quoted, physics in a box, and you mentioned that, maybe I'm getting this wrong, but it's more drifting towards philosophy and stuff. But what I want to understand is, you said there is this observable universe through which you govern, through which laws are made, right? Am I quoting you correctly?
Yes.
So can I also assume there is some unobservable universe that we cannot perceive? Or no, I just want to verify this idea first of all.
Let me just say my quote again. You can believe anything you like. No, don't laugh. Most people believe things which are not part of science, and that's fine. I'm nothing against believing in unobservable universes and unobservable realms. That's fine if that's your taste, but you're not doing science.
But
which doesn't mean
no. But my question is, does science account also for those things? Because you said you mentioned that there are laws. The laws in the universe are changing, and nobody understands how these laws are changing, right? The laws at the birth of the universe are completely different than the laws that are existing right now.
Right? But if I want to make, let me back up a little bit, okay? We don't observe the whole universe.
Yes.
We observe a part of the universe.
Yes.
That's an issue for cosmology all by itself, okay? The only way we can deal with that issue is by either not doing cosmology or doing cosmology in ways that we don't have to presume anything about those parts of the universe we don't observe, okay? Or observing that our region is typical. Okay. Now, when I hypothesize that the laws are different in the past, I aim to make testable hypotheses. I'm not, as long as I want to remain a scientist and not a rock and roll star, I don't want to professionally make hypotheses which are not testable. I'm free to do that. I'm free to speculate, but I wouldn't publish it as part of my scientific work.
Okay. Yeah.
Thanks. Okay, last couple of questions. Okay, well, I guess it's time for a really wacky question then.
Okay.
You're looking very hard at the mathematical framework through which we evaluate physics. Very reasonable thing to do. I got a bachelor's degree in physics and polluted my mind with sort of pure mathematics. And one of the things that always troubled me is that in physics we're using mathematics on a regular basis, but mathematicians have that nasty little undecidability theorem of Gödel's to deal with. Does that ever actually, like I said, I had an undergraduate degree in physics, but I do computer programming, like many people like me. Does that ever come up in terms of how we might view things? Do we have theories that we look at to see whether that undecidability, problem comes up?
It doesn't come up in an important way so far, but it's a question which is hanging around. Let me phrase the question, do we need mathematics, no, that's not my question. We do need mathematics. No. I think mathematics is very powerful and very useful when it's properly understood what its role is. Do we need mathematics beyond that mathematics which is finite and therefore not subject to Gödel incompleteness or uncertainty? There's a subclass of mathematics which is completely finite objects. Is that sufficient to do physics or to model observations and explanations in physics? Do we necessarily have to take on board the part of mathematics which deals with infinite sets and therefore is open to Gödel incompleteness or undecidability? And that's a very interesting question, and people do raise it from time to time, but I've never seen anything useful so far come from it. But it's a question that's there.
I have a comment and the question. So my comment is that I don't think it's quite fair to equate mathematics and mathematical formulas with computing. And the reason for that is that computing, these days at least, concerns itself much more with the state, and especially multiple states. And there is nothing quite similar to the concept of a state of a system in mathematics. Like you said, I mean, mathematics is timeless. So that's my comment. The question that I have is related to that comment is, in your theory of evolutionary sort of nature of the universe, do you account or predict exchange of information between different generations of universes?
So the first point is a fair point. And this was, so I just plead that this was a partly public talk. And so there are subtle issues about computability and mathematics and so forth, and I just did not address those. So that's, the first point is a fair point. The second point is a kind of science fiction-y point. That is, and might somebody in a model of a bounce, say, might somebody be able to shape something falling into a black hole that would be readable, say, in the cosmic microwave background of the universe, the results? And that's that's a science fiction-y hypothesis. It might become, in the future, or the far future, it might become a more interesting hypothesis. It doesn't sound crazy to me, but neither does it sound... to talk about this, I'd have to talk in detail with you about our present models of bounces. There are models within quantum gravity of the details of these bounces, but they're not detailed enough to take on a question like this. But again, this is SETI, so I get to say things I wouldn't say anywhere else. It must have occurred to people to look for information, non-trivial information, in the seemingly Gaussian fluctuations in the cosmic microwave background.
Last question.
It's hard for me to see that laws changing over time is going to make any difference with regard to free will or determinism.
Good. Thank you for that. And do you want to say more?
No, I want to ask another question.
Okay.
So I don't know if you have a response to that, but
I'm just starting to think about these issues.
okay.
Okay, but let me say something that I am willing. Let me talk about qualia, that is just consciousness experiences themselves, these sensations of red, of blueness, yellowness, and so forth. Just at that level. And here I follow Galen's, these are philosophers, Galen Strawson, Thomas Nagel, in wanting a version of naturalism in which qualia can have a real place rather than having to be excluded as figments of our imagination and lies we tell each other the way that Dennett would have it. And I think that in naturalism version 1, where there's no present moment, there's no chance to incorporate qualia as part of the natural world. Because qualia are part of the present moment. The thing which is true of qualia, at least so far as we know, is that they are part of the present moment. So, whereas in a version of naturalism in which the present moment has real and everything that's real is real in the present moment, there can be room for an extension to incorporate qualia of the kind that those philosophers of mind want. So that's as far as I'm willing to go. I think free will is a lot harder of an issue. And I'm not, you've probably thought about it much more than me. Almost anybody thought about it more than me. Okay. You have a second question?
I maybe should pass on and ask you afterwards.
Okay.
The time's up.
Thank you.
Well, no, it's. I think it's time reborn. Everybody, if you haven't got your own copy, including you out in internet land, go out and grab a copy. And Lee, we have a special Are We Alone mug, SETI dark matter that we can pass on to you, and hopefully it brings you some insight when you fill it with sufficiently caffeinated beverages and sometime in the future.
Thank you.
Thanks very much, Lee.